Alright, physics, here we go. Picking up with energy again, right? We just talked about the couple different types of energy, how to apply it down there. What I want to get into today is like an extension of that, right? I mentioned that conservation of energy was a thing, right? So if we know how much energy there is at the beginning of a situation, if something about that changes, then we should be able to figure out what happens later, what that means for later. I'm going to use our goose friend. And by the way, I've been informed that our goose friend is one of two things. Wildly, wildly obese, or a crazy mutant goose. And the reason I bring this up is because geese are only like 7 to 10 pounds, and this goose is like 25 to 30 pounds. So this is two or three times bigger than that even a large sized goose. So this is a truly terrifying flying object. We're gonna run with it because we've already gotten this far. Because our goose is kind of an anomaly, I'm not gonna worry about how these numbers turn out. It's mostly just to like demonstrate how conservation works. We established before. Oh, my pen is really. Oh goodness, why are we? That's better. So we established before that I have 4,859 joules of mechanical energy. So at 40 meters, flying 5 meters per second, that's how much energy this goose has. In the absence of a rocket engine strapped to the goose and air resistance slowing the goose down, the goose will just always have that much energy. So, what that means, let's say that our goose friend dives down to a height of 10 meters. How fast is the goose flying? Right? How fast is our goose dive? So our goose is here, flying at a casual speed, and then, right, he's going to dive. I also found out today that geese are largely herbivores. They largely eat plants. They'll occasionally eat insects, but they basically eat plants. Didn't occur to me. Anyway, so we'll say that our goose has seen something particularly interesting and is diving. Right? It doesn't look like this is conservation of energy, because nowhere does it mention energy again. However, I just said the amount of energy that it had before it dives has to be the same as it is during the dive and even after the dive, which means that the total energy has to equal however much potential energy it has plus the amount of kinetic energy it has. Now, I know that it has 48, 59. This happened earlier today too. This is wild. I can't like draw the number 9 right now, and I don't know why. It's turning into a G. My program is freezing, so that's pretty cool. Something is happening? Hello? There we go. My goodness. Okay. 48, 59 joules. Our goose still has potential energy because the goose is still above the ground. It's 10 meters off the ground. So it still has potential energy, which is 12 kilograms times 9.81 times 10 meters. It also has kinetic energy, which is 1 half times 12 kilograms times v squared. And there is our how fast. Right? I have this v squared. Now, I have some math to do, so I'm going to grab my calculator, aka my phone. I need 12 times 9. Nope. 9.81. Nope, that's wrong. 9.81 times 10. This is 1177. So I know that 4859 joules equals 1177 joules plus 1 half of 12 kilograms times v squared. If I'm solving for v, I gotta subtract. So I'm gonna do 4859 minus 1177 is 3682 joules. That equals 6 kilograms, that's half of 12, times v squared, which means v squared is 3682 divided by 6 is 613.6 repeating, but then I have to take the square root, which means that v is, give or take, I'm going to do my scientific version, v is, give or take, 24.8 meters per second, or 50 miles an hour. And again, for our mutant goose friend, it's not a big deal. It's not a big deal. I'm sorry, emails. A mutant goose can go 50 miles an hour and not worry about it. A regular goose probably wouldn't. Although, I mean, when they're migrating, they might get pretty fast. This was a complex one because I gave you funny numbers over here. If I were to do a more typical example of what you might see when you have to apply... Oh my goodness. Computer? Hello? Okay. What you might see when you have to apply conservation of energy, you might see something more along the lines of a ball is held at a height of 5 meters above the ground. It is dropped and falls to the ground. There's ground. There we go. How fast is it going immediately before hitting the ground? Right. So we take this ball and we hold it up in the air, and then we let it go. It's dropped, right? That tells us something. It's dropped, and it just falls to the ground. How fast is it going immediately before hitting the ground? This doesn't look like conservation of energy. However, what I can say here is energy at the beginning equals the energy at the end. And if I look at this and I think, like, what kind of energy does this ball have at the beginning of the situation? Well, it's being held 5 meters above the ground. So it must have potential energy, and it's being held, so it's not moving. So it only has potential energy, which is mgh. At the end, our ball is moving, it's falling. And immediately before hitting the ground, we're talking about like that moment right before it hits the ground, so its height is basically 0. It no longer has potential energy, but it's moving fairly fast. So it must have kinetic energy, which is 1/2 mv squared. I have to look for that velocity, and it looks like I need mass, sort of. Look at the equation, and look, mass on both sides, it's the same ball both times, so I can actually cancel it out. I can cancel it out, and now I can solve for v. I know that the acceleration due to gravity is 9.81 meters per second squared. I know that it's 5 meters off the ground, and that's going to equal 1/2 times v squared. So this is 2 times 5 is 10, times 9.81 is 98.1. Meter squared per second squared are the units here because it's v squared. I need to take the square root. So v is about 9.9 meters per second. I just used conservation of energy to find a velocity because I kind of recognized, understood that the energy at the beginning must equal the energy at the end. I think I said this in the other video, but this is what I meant when I said energy is something of like a get out of jail free card. Because if you're not sure how to get something, right? This looks like, I don't know, maybe there's another way to do this. In fact, there is another way to do this. You could have done this with the timeless equation, and I'll show you how in a little bit. Um, but if you're not sure, let's say you've completely forgotten everything, but like energy exists. Try energy and see what happens. Chances are energy in some form or conservation of energy will get you there. All right. Now, what I want to do is start a lab the next time you're in class. So like C-Day, right? Fully remote students, I'm going to try to get a better version of the video. And actually, I think to fully remote students, you'll probably be able to do this lab at home, even on your own, as long as you have something that you can drop and will... you'll see. When we do the lab on C-Day, you'll see. All right. In the meantime, tonight there are some questions on energy that I would like you to do. It could be a little bit of conservation. It could just be some basic sulfur kinetic, sulfur potential. But it's just so that you see some wording, because I do want to quiz next week on energy. I'll probably do it the same way. I'll probably do it online again. That online quiz works pretty easily. So, but yeah, conservation of energy. Basically, again, energy at the beginning all has to be there at the end. It could be in different forms. It could all be in one form. But no matter the case, conservation of energy is a good kind of trick to have in your back pocket. Right? Until next time when we start a lab, I will see you. In the meantime, be good. Stay safe, kids. I'll see you soon.